Hi, this is Mrs. LaBarbara. This is Physics Chapter 8, Video 5. Today's topic is electric field around point charges. The objectives are know the similarity and the difference between electric force field with gravitational force and field. Know how to determine the direction of electric field. Know the rules of drawing electric field lines. To understand, electric field strength is a vector that is inversely proportional to distance squared from a charged object, and to be able to determine both the magnitude and the direction of electric field, and be able to draw the field lines. So now let's take a look at electric force and gravitational force. Both forces are field forces. Field force means non-contact force. You don't have to touch in order to feel it. Gravitational force is created between any object that has mass. So the mass of the Earth exert an influence affecting other mass, which were in the surrounding neighborhood. So if you have a satellite, you can launch a satellite. The satellite will go around Earth because that satellite is in gravitational field. Similarly, anything has charge will have an influence around the space around it. So it will affect any other charge which is in that space. And that space, we call that electric field. So electric field and the gravitational field concept. So how can an apple reach across the space and falls toward Earth? We said because this Earth creates a gravitational field. It has effect on the mass of the apple, and it will pull toward it. So any object has mass will be experience this effect of Earth. Similarly, anything has charge will have an effect in its surroundings. It will affect the other charges. Anything has other charge in that space will make the other object either push it away or attract it. Electric and gravitational field. So gravitational field strength, we have learned this before. Gravitational field strength is force per mass ratio. So G equals Fg over m. So if you use your weight divided by your mass, or I'm using my weight divided by my mass, we should have the same number. On the Earth's surface, G equals 9.81 newtons per kilograms. And if we move away, your weight will be a little less. So G is a little less. As you move away from the Earth, gravitational field strength decreases. The direction of the field is toward Earth. Similarly, electric field strength is defined as the electric force per charge ratio. So it's a ratio. The direction of the field is a vector that is the direction that a positive test charge is pushed or pulled when in the presence of electric field. So it is really away from the positive and toward the negative. It's away from positive is because if I put a positive charge here, it's going to repel the positive. If I put a positive charge here, it's going to move along the line. If I put a positive charge here, it's going to move along the line. Toward the negative is the same thing. If I put a positive charge over here, it's going to move toward a negative. The source of electric field and the source of gravitational field. So the source of gravitational field, we know it's the mass of the Earth. Because the Earth has such a big mass, it produces a field around it. And to find a field, we can use two ways. We can figure out like your mass or my mass or the calculator mass, we can figure out its weight. We just do a ratio to find the G at that location. Or if we don't need, obviously we don't need your mass or my mass to know the gravitational field is there. So if there's nothing around Earth, Earth still produces a field. How do we find that field? That field is, we use G times big M over R squared. This is the mass of the Earth and divided by distance squared. So that is how another way we can find gravitational field strength. So it is inversely related to the square of distance. As you move away from the Earth, g is getting smaller and smaller. Similarly, electric field does not depend on any test charge. So my mass or your mass or the mass of the calculator is kind of like test charge. So the electric field does not depend on the test charge. It only depends on the source charge. In the same way, gravitational field depends on the mass of the Earth. This mass of the Earth is like the source charge, like big Q, that's a source charge. So E, there are two ways to calculate E, the ratio on the test charge, the force on the test charge divided by the charge on the test charge, or we can use the amount of source charge and how far away from the source charge to find E at that location. So E is also inversely related to the distance squared. Electric field strength, we said there are two ways to find it, right? We can use source charge, K times Q over R squared, or we can use test charge to find what is the force on the test charge and do the ratio. So in both equations, E is electric field strength, its unit is Newton per Coulomb. Little q is the test charge. Big Q is the source charge. So little q and big Q are different. Little q is kind of like my mass or your mass. Big Q is the mass of the Earth. Fe is the force between the force acting on the test charge. K is the constant and R is the distance from the source charge in meters. So electric field strength depends on the source charge only. It has nothing to do with the test charge. It's almost like little g 9.81 does not depend on your mass or my mass. Depends on the mass of the Earth. So note there are two charges here, source charge and test charge. Electric field strength is not dependent upon the test charge at all. Electric field strength only depends on the source charge, big Q, and how far away from that charge, R, or D, sometimes we use interchangeably. Let's do an example. What is the magnitude of electric force acting on an electron located in an electric field with the intensity of 5,000 Newton per Coulomb? So let's see what we know. We know E, we also know Q. How did I get Q equals 1.6 times 10 to the negative 19 coulombs? You read the question. This is an electron. Electron has the charge on an electron is elementary charge. One elementary charge is 1.6 times 10 to the negative 19 coulombs. You're trying to find force. So look at your equation, the equation we have just learned. You substitute everything in. Your force is 8 times 10 to the negative 16 Newton. Another example. So the diagram represents uniformly charged rod, which graph represents the relationship between the magnitude of the field intensity and the distance from the rod as measured along the line AB. So we know the field is inversely related to the distance squared. So this is inverse squared relationship, C. Let's take a look at this, the direction of electric field vector. So we already know direction of electric field vector is defined as a direction that a positive test charge is pushed or pulled when in the presence of electric field. So electric field vector would always be directed away from the positive and toward a negative. So this is positive going away and negative is toward. That's a field called the field lines. Let's take a look at this example. So two small metallic positively charged spheres A and B are separated by a distance 0.4 meters as shown, which arrow represent the direction of the resultant electric field at point P due to charges in spheres A and B. So A is positive, it produces a field away from A, so kind of going in the upper right corner, that way diagonally, upper right. Similarly, the field produced by B is going away from B, so it's going to go upper left direction. Electric field is a vector quantity, so we have to add these two vectors together. The sum of these two vectors is going to go upward. So the answer is 2. Electric field lines or field maps. So we know electric field is going away from positive, coming toward a negative. So here is a field between positive and negative, looks like. Here are the field between the negative and negative. So coming toward a negative. So electric field basically in the middle is 0 because the field over here cancels out by the 2, always pointed toward a negative. Here, if you have 2 positive charges, it's going away from the positive. So this is the field produced by 2 positive charges. Again, right in the middle, the field cancels out, so you have 0 field right in the middle. How do we draw this field? There are, besides it's going away from positive, coming toward a negative, the line must begin on positive and terminate as a negative charge, surrounding more charged object by more lines. As you can see in this diagram, we know the charge on the right must have more charges than the charge on the left because there are more lines. Draw the lines that are perpendicular to the surface of the object. So all the lines are supposed to be perpendicular to the surface. And one thing you need to know is electric field lines never, ever cross. So it does not cross at all. You can be very, very close to each other, but they don't cross each other. Let's do another example. So this diagram shows electric field in the vicinity of 2 charged conducting spheres A and B. What is the charge on each conducting sphere? So we know the electric field line starting from positive, ending with negative. So A is positive and B is negative. So A is positive and B is negative. The answer is 2. That's it. Thanks.